Today we're going to talk about predicate calculus and some more complex circuit design. In order to do more complex circuit design, first we're going to talk about binary numbers and what they really represent. So binary numbers work just like decimal numbers, except the base is 2 instead of 10. So normally when we think about numbers, we think about the ones place. This is how they taught us when we were kids. The ones place, the tens and the hundreds, and so on. And then if you want to figure out what a number is, you would take 5 times 10 cubed, which is 5,000, 2 times 10 squared, which is 200, plus 3 times 10, which is 30, and 1 times 1. So this will be 5,200s, 30, and 1, all added together. So in the same way, we can figure out what a binary number is in decimal. So for example, if I had 1101 in binary, then I could compute what it is in decimal by adding the places. So this is the 0th place, 1, 2, and 3. So we take a 1 times 2 cubed. We add that with 1 times 2 squared. We add that with 0 times 1, 2 to the 1, and 1 times 2 to the 0. And that gives us 8 plus 4 plus 1, which is 13. So let's do another example. Another example is if I had in binary 0, 1, 1, 1, then this 0 is the 2 cubed place, but I don't have any. It's just 0 times that. So it would just be 2 squared plus 2 plus 1, which is 4 plus 2 plus 1, which is 7. Okay, that's how we represent numbers in binary. So if you want to figure out what a binary number is, you can convert it into decimal by multiplying whatever's in the place by what that place stands for. So let's try binary addition. Okay, and let me try not to confuse you. We've been talking about ORs as pluses, but they really have represented ORs. But now I'm going to talk about addition like real arithmetic. Okay? So if I want to take two binary numbers, like 1 and 0, and add them together, what will I get? 1. How about 0 plus 0? 0. What 0? How about 0 plus 1? 1. And 1 plus 1?
0. 0.
It's 2, right? How do we write 2 in binary?
1 0.
1 0. In other words, it's 0 carry a 1, right? So if I had more columns, I would carry the 1 instead of writing it right next to it. Right? So let's do some bigger binary problems where we have more than one column. Y'all are smart. Let's do an even larger one. Okay, so we're going to do just like we do addition with decimal numbers. We'll start from the right and go to the left. So we add 0 and 1, and we get 1 with no carry. So the carry is a 0. And then here we add 0 plus 1 is 2, which is a 0, carry the 1, right? And then 1 plus 1 is 3, which is 1 carry a 1, right? 1 carry the 1, and the 1 falls down. So this is our final answer. The other way you could figure it out yourself is to write this one in decimal, which is 6, and this is 7, and this should come out to be 13, and that's how you can check your answer. And we actually did do this, and amazingly enough, that was by accident. I came out with 13. Okay, let me teach you a little trick for doing binary addition. Because sometimes it's confusing, that 1 plus 1 is equal to 1 carry a 1. Okay, but I know that you know how to do addition really well with regular decimal numbers. So I'm going to teach you a little trick, and the trick is this. The trick is to change 1s into 5s. So let's redo this same addition, but change the 1s into 5s. And then at the end, I'll change the 5s back into 1s. At every point, I'm always going to change 1s into 5s, and then at the end, I'll change them all back. So here I add 0 and 5, and I get 5. Then I add 5 and 5, I get 10, which is 0, carry the 1, right? But 1s change into 5s. So I get 5, 5, and 5 is 15, which is 5, carry the 1, it changes into a 5. And then I change them all back, and I get 1, 1, 0, 1. Here. Why does the trick work?
So you're dealing with decimal, you know.
You're breaking decimal down into a binary system.
That's right, because 5 is halfway up to 10, right? And 1 is halfway up to 2. So the way the things move between places should work the very same way. If I do half of the base in decimal, it should work the same way as adding in binary. That's why the trick works. Okay, so it was important to do this because we want to design a circuit that will do addition for us. Why would you want to do that?
Make a calculator.
Make a calculator. You have to do to count, right? Also to do arithmetic in your computer, right? So in your computer, you have something called an arithmetic logic unit. And it will take two binary numbers and add them. And it's a really extremely important part of a computer. Because you can't do very much if you can't do addition, right? So we need to be able to design an adder. So we're going to make an adder circuit. So first, let's just design one for 2 bits. So like one column of addition. Because if I were to split a task of adding, I would do it column by column because that's the procedure I already use as a person. And it's the most logical way to split it up. So I'll try to design a circuit for one column of addition, and then hopefully I can use it for any column, right? Okay, so in a column, I have 2 bits, plus I might have a carry bit, right? So let's say x1 will be the top row, so we'll be doing like x plus y and a carry. Okay, so we'll put x1 because this will be column 1. Okay? We'll have y1 and c. I'm going to put c0 because this carry came from a previous column if there was one. Okay? And then I'm going to have 2 outputs. What are the outputs? The outputs should be the digit at the bottom of the column and the carry for the next column. So I'm going to call that the sum bit and the next carry, which I'm going to call C1 because it came from column 1. Then these are my inputs, X, Y, and C0 are my inputs. So I can go ahead and fill them out like I normally do for binary. Since there are 3 of them, I have 8 rows in my truth table. And then I just have to figure out what happens for every single row when I do addition. So in the first case, I have all zeros. And that's easy. I know that adds up to be 0, and I don't have to carry anything either. If I have just 1, 1, as in the second and third rows, then I know my sum bit's going to be a 1, and I carry what?
0.
I carry a 0 in both of those cases.
How are you getting S and C1 again?
This is the digit that goes, if I'm doing this addition right here, that's the S, and this is the carry. So these are my outputs.
Okay, so you're just reading across. Okay.
So I'm reading it across. So I'm reading my values for X, Y, and C0, and then I'm pretending I'm plugging them into a column of addition, and what would be my digit that comes out would be S, and I would have to carry C1.
Okay.
So here I'm adding 0 plus 1 plus 1, And so that's 2, so I know my sum digit is going to be 0, and I have to carry a 1.
Right, okay.
In the next row, I have just 1 1, so my sum bit is a 1 and my carry is a 0. In the next 2, I have 2 1s, so that I know those are both 0, carry 1. And in the last case, I have 3 1s, which add up to 3, which is 1, carry a 1. So in this circuit, I have 3 inputs and I have 2 outputs. And I could make a chip and put all of these things on a chip and then hopefully have it manufactured. So anytime I had to do a column of addition, I could just plug this chip in. Okay? So we're the engineers. We have to design the chip. So we have to figure out what logic gates go on the chip. Okay? So that means that we have to write disjunctive normal form for each of these. Remember that? So for the S bit, let's write our disjunctive normal form for that. Let me zoom here. Oh, wrong way. So we have to write our minterms for that. So S is equal to, it has a 1 where x1 is false, y1 is false, and c0 is true. It has a 1 in the next case where x1 is false, y1 is true, and c0 is false. It also has a 1 where x1 is true, and y1 and c0 are false. And the last one, it has a 1 when all 3 of them are true. So I should have 4 minterms because I have 4 1s in my column for S. And also, when I look at this, this should make sense in terms of what my sum bit is. You know it should be a 1 if exactly one of the inputs is a 1, right? So each of these first 3 terms has exactly one of the bits as a 1, and that makes me feel better. Okay? And then in the last case, all 3 of them are 1s, and that feels okay too because I know that then if all 3 of them are 1s, that makes a 3, which is 1 carry 1. So I just double-checked by knowing what I wanted. I just double-checked S to make sure that I wrote the right equation. Now I have to write one for C. Actually, let's go ahead and make a circuit for this. Okay, so if I had to make a circuit for this, I could write it directly, right? So if I was going to use multiple input gates, how many do I need?
2, 3, 4, 5. 5.
I need 1 for each of the minterms, right? And I can use a giant OR gate to OR all of them together. So I need 5 gates. So I'm making the gates for these, putting the knots on, and I skipped. Oh, I don't need 5 AND gates. I need a big OR gate here. So there's a circuit for S. And by the way, this whole problem is given in Chapter 9 in the Haggerty textbook, the little blue one. That's your textbook. Chapter 9 has an application section, and this entire problem is given in there. So this is without any reduction, right?
Yes.
So we could have reduced it and made a circuit for it, but that would have required more work. So just leave it the way it is. Now let's write a, has everyone finished looking at this? Yes? Okay. Now let's look at our carry bit and figure out when we need, what minterms we're going to need for that. So again, we have 4 ones in our column for C. Our first one is when x1 is false, and y1 and c0 are true. And if you notice, we're going to have terms where 2 of the bits are 1s, right? Because we should have to carry if at least 2 of them are true. So when we have x1 is true, y1 is false, and c0 is true, we have another one. Then we have a one where we have x1 is true, y1 is true, and c0 is false. And in the final case, where all 3 of the variables are true. And again, I can double check that and see that in every case, 2 of the bits are true. And so I feel good because I know that that's when I need to do a carry, and there are no other times when I need to do a carry. So then as soon as I'm done with the minterms, we're ready to make a circuit for that. So I can just tell you how, if this were a homework problem, and you just wrote this circuit in disjunctive normal form using the minterms like we just did, it would be very easy for me to check the answer because I can just check and make sure that you have a not in the right positions on these gates. Because as I just said, we know that the carry bit is true when at least 2 of the bits are true. So all of these gates should have at least 2 of the bits true. All of these get ORed together to get my final output of C. So you know how to label the rest of the diagram, so I won't waste your time doing that. We worked this problem just C1. That was C1. Thank you. We worked this problem just as a representative of some of the things that you're going to have to do when you do the test. So you will be given a function, and I'll ask you to write a truth table for it, and then you have to make a circuit for it. And I won't ask you necessarily to reduce it. Now, the other reason why we did this problem is because if I had to make a circuit that did addition for more than one column, then I might want to reuse a circuit that I've already designed, right? So I just made a circuit for S, and I made a circuit for C1. What I'm going to do is I'm going to pretend that I had that circuit, those 2 circuits, I had them put on a chip, which I'll now consider to be a black box. And this is my adder. And by the way, just for anyone who looks at the book, they call this a full adder because it has a carry and the inputs. If it doesn't have the initial carry, it's called a half adder. But I don't like to do things halfway, so we're going to do the full adder. Okay. So that takes as input x1, y1, and c0, and as output we get S. Let's just put c0 over here, and we'll put c1 down here. So we'll get S1 and C1. So let's suppose that we wanted to build a circuit to do 2 columns of addition. So first, let's write down what it looks like to have 2 columns of addition, and then we'll figure out how to make a circuit using this black box. Because it's a chip, now I can use as many of these chips as I want to. So I can write this here. We said that we had x1 and y1 and c0 for one column, and then we had s and c1 like this. So in the next column, I should have some more bits. The top row's x's, right? So this should be x what? X2, just anything besides x1, right? Because it's a different variable. And this will be y2, and that was s1. So this is going to be s2 as the result of that. And then we're going to have C2 as the carry. So if you look, our first adder will take the first column as inputs and give S1 and C1 as outputs. My second adder has what as inputs?
X2, Y2,
C1.
X2, Y2, and C1. And then I have outputs S2 and C2 again. So if I draw another adder here, let's put a piece of paper here. I know that my outputs are going to be S2 and C2, and I need to put X2 and Y2 here. And this is a carry bit. This has to be C1, but that comes from my other adder, right? So I'm going to take this wire and I'm going to hook it right up to this wire. So this is sort of my adder number 1. This is my adder number 2. So this does the first column. This does the second column. And I've just shown how we can add them together to make a 2-column adder.
What's that C in the middle? Is that a
This
C?
C1.
Yeah, C1.
This is C1. This is the output of the first adder because it has a carry bit and a sum bit. It has a sum bit 1 and a carry bit 1.
Okay.
Because I put both of those circuits in there. We made a sum circuit and we made a carry circuit. We would put both of them in the black box and hook up these inputs to the circuits that we made. So there'd be 2 little circuits inside this box, and one would give me this output, the C1 output, and one of them would give me the S1 output. And in here it has 2 circuits also. It would take these as inputs, and one of the circuits would give me S2,
So
and one of them would...
C1 as the input to the second adder?
That's right.
Okay.
So this is nice because once you've designed a circuit, you can reuse it again for something else. For example, we could have made part of our sum bit, we could have made it with exclusive OR, because that's a circuit that you could use and reuse because someone's already designed the logic for it. So since there's already one, and the truth table looks like exclusive OR if we look at it. Let's take this off. If you look at that top part looks like exclusive OR, right? The second part looks like the opposite of exclusive OR. So we could have used some exclusive OR gates to make S in the first place. It's not wrong not to. It's just that we didn't use some. So I'm just saying that anytime you have something that you've already designed, you can use it again. And that might seem really obvious, but if you're doing your homework and no one told you that, you might not think of it. So if you've already designed something, you don't need to do it twice. You can draw a black box and say, put my previous work inside this box. And the reason why that's important is that your next homework assignment has you designing a circuit where you're going to be designing a circuit and then you're going to reuse it twice to build a more complicated circuit. And let me tell you a little bit about that problem. Your next homework is homework 3, and it is posted online. I posted it this afternoon. And the very first problem on there is to design a multiplexer. And I'm not going to do that problem just now. I'm just going to tell you what a multiplexer is. Okay? How many people have heard of multiplexers? Just one person. Okay. A multiplexer is a really cool circuit. What it is if I had a multiplexer, let's say I had a 2-bit multiplexer. This is going to be my control bit. So I'm going to have X0 and X1, and I'm going to have control bit C0. This is going to be an input also, so it really goes in. These all go in, and this one goes out. And the output bit is going to be either X0 or X1, whichever bit C0 tells me. Okay, so C0 is my control bit. So my output's going to be if C0 equals 0, then output X0. If C0 equals 1, then output X1. So it's like a switch. So it's as if I had a bunch of lines so I had 2 lines here, and if I flip the switch up, it's going to give me X0. If I flip it down, it'll give me X1. So a multiplexer is basically a switch. And what are switches useful for? Lots of things. Okay, so wouldn't you like for stoplights to have switches, right? You definitely want green lights on one side and red on the other, right? So I would want to be able to switch in between those. So I'd always want them to be opposites, and I would switch between the state of this being green and this red, and switch and have this green and red, and I don't want any other kinds of states, right? I mean, we have yellow in there, but that makes it more complicated, so we're ignoring the yellows.
Is C0 here an input?
Yes, it is. It's an input. That's why I drew the little arrows going in, just to make sure that you knew that that's also an input. But it's usually called a control bit. And usually it's tied to a clock. And why do you think it might be tied to a clock?
So it switches automatically?
So it switches automatically. And if a clock were hooked up to a multiplexer and was switching automatically, what could you then use the multiplexer for? What does your computer use a multiplexer for?
Monitor off after so long.
I'm not sure if it would do that. Might.
Processing queues and stuff?
Yes. If I were processing queues or something, basically for scheduling. So if I'm trying to run 5 things on my computer really only runs one thing at a time. Everybody knows that, right? Okay. Most of us don't have parallel machines on our desktops, and even if we do, they're going to run one thing at a time most of the time. But that means that in order to make you think that you're running lots of things, it does a little bit of this one and a little bit of that one and a little bit of that one. So a multiplexer is tied to a multiplexer, a software multiplexer is tied to a clock that says, okay, now I'm going to do part of task 1. Now I'm going to do part of task 2, and then task 3, and then I'm going to go back and do 1, 2, 3, and then keep going back and forth. And I need to switch it and not ever let task 1 and 2 run at the same time because I only have one processor. So when you have resources that are limited, it's really good to have something like a multiplexer that just selects one of the lines. They also have, if you know anything about telephones and the way they're hooked up, they have switches in telephones and switches in the internet because you can only use a wire you can only use data on the wire for one thing at a time. You can send, little data packets and have multiple data packets from different sources on the wire, but a multiplexer is going to tell which one gets to use the wire right now. And then you switch, and someone else gets to use the wire for a second, and then you switch, or really a millisecond or some nanosecond, very, very small amount of time. So the internet and your phone all use things like multiplexers to switch between using resources that are limited, that can only be used by one thing at a time. So you're going to design a multiplexer. So what would your first step be in designing a multiplexer? Making a truth table would be a good idea, don't you think? You could either make a truth table or you could figure out how to write a logic statement that represented this, right? I would make a truth table, and I might try this too, and double check and make sure they did the same thing, right?
What do you mean by output is x0? Does that mean...
So it's as if I have a little switch in here. Let me draw a little diagram. I'm going to put a little node right here and a little node right here. And C0 is going to make this little switch move. And if C0 is 0, I'm going to have like a connection between there and there. And so there's like if x0 is 1, then a 1 will come all the way through. Okay? And if C0 switches and moves to here, then the x1 can go through and the x0 can't. So whatever x0, x1 happens to be at this time, it'll come through if C1 is set to 1, C0 is set to 1. Right? So whatever it's set to, that's how I would do it. Now, if I were allowed to use switches, then I would be done designing my circuit, right? But we're not allowed to use switches. We have to build switches with gates.
So it's going to show whatever the value of x0 is, 1 or 0?
Depending on the control bit. The control bit will tell which one I'll show. So if...
Yeah, but you're just stating that your control bit is whether the switch is which switch is getting the electricity.
That's right.
But isn't there a 1 or a 0 in the x bit, an x1 bit?
Yes. So if there's, say that for instance I'm on this side, okay? That means that C0 equals 1. That's one of my inputs. C0 has to have a value. That means that C0 equals 1 if it's in this position. Now, if x1 is false, then a false comes through as the output.
Right, okay, that's what I was asking.
If x1 is true, then a true comes through.
Okay, that's what I was asking.
So the control bit doesn't give any electricity, it just makes a connection.
Okay.
So all of the outputs are going to come from the x0 and x1 inputs. and C0 is just going to pick which one.
Okay.
Okay, so I would make a truth table for this. Okay, so we said that if C0 is 0, then our output is going to be x0. So for the first 4 rows of the table, I'm going to have what values?
0, 0, 1.
0, 0, 1, 1. Now we also said that if C0 is set to 1, then the output's going to be the same as
x1.
x1. So then the values here are going to be the same as x1, which is 0, 1, 0, 1. Now, I could design the circuit by doing minterms and drawing it, or I can make a much simpler circuit by looking at this and seeing that I can separate this into 2 cases, half of it where C0 is false and half of it where C0 is true, right? And then I could OR those things together if I wrote a function for this and a function for this. I'm not going to do that. That's just a hint. Okay? If you don't simplify it, you will not lose points on your homework. But if you do, you'll think it's really cool. Okay? So that's just a hint if you want to make a simple circuit for that. Actually, I'm only not doing it because I don't want to do your homework for you. Because once I do that, then drawing the diagram would be really, really easy. So let me show you on the sum bit from the adder how we would do that, because I think it's useful to know. So in this case, let's suppose that we're going to split the sum bit up into 2 cases. The first one where x1 is false, and the second one where x1 is true. So the first half of the table has x1 false, and the second half has x1 is true. Right? And then I can look, if I ignore the first column and then just look at y1 and c0, that looks like a regular 2-input truth table. Right? And my output looks like exclusive OR. Right? So I could say that in the case where I have x1 is false, my output looks like y1 exclusive ORed with c0. In the bottom case, it looks the same. It looks like a truth table for y1 and c0. And this looks like,
Exclusive NOR.
it looks like the NOT of the exclusive OR, right? So I'm going to put y1 exclusive OR c0 and then negate that. And then in order to create this function, I would just OR these 2 items together. Why does that work? Why doesn't this function mess up that one?
Because it's an OR.
Well, this is an OR. So you might think that the ones from here could combine from the ones from here and put some ones in the middle. The reason why it doesn't is because it's ANDed with x1 is false. So these things only affect s whenever x1 is false. And this term only affects s when x1 is true. So this one exactly corresponds to the top part of the table, and this one exactly corresponds to the bottom part. And that's why I can OR them together and not worry about whether any ones from this function are going to mess up this, because I know that this will be all zeros in the top half. You can verify that for yourself at home if you're not sure exactly what I was just talking about. So you can go home and figure out how does this work. Okay? But it works in a similar way that we did the minterms, right? A minterm was only true in exactly one row of the column, right? Well, x1 is false for all 4 of these rows, and it's not false any other time. So this function here has all zeros in the bottom part, so I can OR it with something else and let let the bottom part have a function of its own. Okay, so that was a trick that is absolutely not necessary for you to know, but you'll probably use it later if you do any circuits at all.
So if you were basing it on rather than x, if you were basing it on y, would you get 4 of those and vice versa?
Yes, or if I wanted to base it on y, I would probably rewrite the truth table so that the y would be on the left,
Right.
so I could just use not y and y in 2 separate functions.
So it's sort of like factoring it out.
Yeah, it's like factoring out the x. That's what I did. I looked at just half at a time and was ignoring the x. And I knew that in the first half of the table, x1 is false, and in the second half, x1 is true. That's exactly right. We were factoring out the x1. Are there questions about this? So your homework problem for the multiplexer, you will have to make the circuit for a multiplexer, and you're going to have to make a circuit for a multiplexer that has more inputs. So you'll have to make the stuff that goes inside this box, where you have 2 control bits and 4 inputs. And you'll need to make it, I've asked you to do it on your homework 2 ways. I've asked you to make just a straight circuit from the truth table for this, and also by using 2 smaller multiplexers that you already designed. So you can also make one of these using your little multiplexers that had just 1 control bit each. So this is like a big M. So you can use your 2 little m's to make the big one. Okay? I'm sure you'll have questions about that next week after you try to do it. Yes?
Now you said that was homework 3?
Yes.
Okay.
The homework that you just turned in is homework 1 and 2 together.
Oh, okay. I didn't realize that.
I didn't label it on there, but it counts as 2 homeworks. And I did that because we started doing homeworks a little late. But so it's still going to add up to 10 homeworks, but you don't actually have a homework that's labeled as homework 2. So the next thing we're going to work on is predicate calculus. So we got to take a little break from logic by doing logic circuits. So we got to take a break from the proofs just for a few minutes. But now we're going to go back to some logic again. So remember that when we first started logic, we had some statements that weren't propositions. They were things that we couldn't tell whether they were true or false, so we couldn't use them in logic. So statements like that were things like x equals 5. And so that's not a proposition, because we can't tell whether it's true or false just by looking at it. But if I knew a value for x, then that would be a proposition. So 1 equals 5 is a proposition. It's a false one, but it is a proposition. There's another way we can talk about propositions, make x equals 5 into a proposition. And that is to say, we might say something like, for all x, x equals 5. So this is a proposition. And what's its truth value? Is that a true statement or a false statement?
You don't know.
No matter what x value I plug in, do I get x equals 5? So if I set x equal to 1, I get 1 equals 5. Is that true?
No.
It's false, right? 1's not equal to 5. So this statement is a false statement. But it's a proposition, so we've actually converted it into something that we can do logic with. Because we couldn't do any logic with x equals 5. Now we can actually do some reasoning about things because we know that this statement is false. It's not true that every x, no matter what I plug in, x equals 5. Now, how do you know what kinds of x's to plug in? Does anybody know? I could plug in dogs, right? Because I didn't say. No one told you what you could plug in, right? So when you see something like for all, you need to ask, well, from what set? Okay? So we're going to have a universe. It's called, this is the math term for it, the universe of discourse. And so in this case, I would want to say, perhaps I might say that x is the integers. So I'd really write, if someone were, a mathematician, I would say for all x, and this symbol means is a member of, or simply in, z, and z represents integers. For all x in z, x equals 5. That's my predicate, and it is false. So a predicate is a statement that would be a proposition if you could plug in a value. So it's basically a function. It's a logic function. It has inputs and it has logical outputs of either true or false. So let me write that down, that a predicate is a function. And we always have to have a domain or a universe of discourse for my variables. So we found two ways so far to make statements into propositions. So we could plug in values. If we have a statement that has variables, we can either plug in values for the variables, or we can say the statement is true for all values of the variables. And does anybody have any other ideas of how we might make a statement with variables in it, how we would make it into a statement that's either true or false?
It's true for some.
That's right. We could say that the statement
Or at least one.
is true. That's right. For some, or at least one value. So in logic, we're going to consider some and at least one, we're going to consider those as the same. Because some, in English, a lot of times we're going to think it's like more than one, that it has to be at least two. And some people might even argue with you that it needs to be at least three if you're going to say some. But in this class, some means at least one.
At
Okay.
least including one?
Yes, at least greater than or equal to one. At least one means one or more. Okay, so we have, as you may have guessed, we have funny ways of writing for all and at least one, because it wouldn't be torturous without them. So for all, we would rewrite for all x, x equals 5. First of all, we would define a predicate. We would say P of x is that x equals 5. That's my predicate, P of x. Then my predicate statement would be for all x, P of x. So this statement, this upside down A means for all. And someone invented that a long time ago, and we're going to have to use it. So we also have a way to write there exists. and that is a backwards capital E. And so the way I remember these is all has an upside down A and exists has a backwards E. And maybe they would have made the E upside down, except it looks the same upside down. So they had to make it backwards. Okay, so these are how we write predicates. And now these are propositions. This is a proposition because it's either true or false. Either it's true that for all x, p of x is true, or it's false. And there exists x, p of x is either true or false. There's either one or there isn't. And I should be able to check. So in this case, when p of x is that x equals 5, for all x, p of x, we already said was false. What about there exists x? That's true, assuming our universe of discourse is still the integers. X equals 5 is our example that makes that true. So in this case, if this is true, I should be able to write down the value that makes it true, right? So that's a good habit to get into. If you have a there exists that's true, it's a good habit to just write down the value that makes it true so that when you look at it again, you can assure yourself that it really is true. If you can do it, sometimes you can't. Okay, and so since these are propositions, they work just like other propositions. So once I've made a predicate into a proposition, I can use it just like I use regular propositions. So if for example, I could use De Morgan's with these. Okay? So if I had for all x, p of x, and there exists x, q of x, each of these values is propositions. So I could apply rules to it. So if I put a not on that and I want to use De Morgan's, I can do it. Because each one of these is a proposition. It's just a variable. So De Morgan's on this would be not the quantity for all x, p of x. Change the and into an or, and not the quantity there exists x, q of x. So that's using De Morgan's rule, and most all of our rules can be used that way. Let me just tell you one convention so you don't ask me later. Where do you think the for all x in that statement applies?
Left to right.
It applies to every single x that comes after it. So I don't need to write parentheses. Although some of you may feel better if you write parentheses. I don't need to write parentheses because the x applies until I redefine it. If I redefine it, as in this statement up here, this x is a different x than that one. Okay, so this is going to work just like variable scoping in your programming. So this is the definition until I redefine this variable. So I don't need parentheses for that. Okay, now, what does this mean? Okay, let's say that p of x is, I'm going to use my purple shirt example again. Okay, so we're going to say that p of x is that x is wearing a purple shirt. And we're going to say that q of x is that x has a giant Q on his shirt. His or her shirt. And our universe of discourse is going to be people. And we'll just say that it's people in this room, just to make it something we can talk about. Now, what does not for all x, p of x mean in English? The way to figure it out is to write for all x, p of x in English and then negate it. Okay? So for all x, p of x means that everyone in this room is wearing a purple shirt. So we're just going to do for all x, p of x, everyone is wearing, I'm just going to leave everyone, I'm going to leave the in the room off, a purple shirt. And then if I want to negate that, the first thing I would do is say not everyone is wearing a purple shirt. Right? That's one way to write it. So you can write not everyone. We just don't usually talk like that because it's a little hard to figure out what you mean if you say not everyone. But you all know people who do that. You know, they make a joke like, not everyone thinks that money will buy everything, right? So people might say something like that, but we also want to figure out how to say it in another way so we don't have a not and an every in the same sentence because it's kind of confusing, right? So how many people have to not be wearing purple shirts to make this false?
Just one.
Just one. So I could say there's at least one person that isn't wearing a purple shirt. That would be the same as not for all x, p of x, right? That's the same as saying not everyone is wearing a purple shirt. So this is writing the English directly from that. So not everyone is wearing a purple shirt is just writing the English from not for all x, p of x. Then if I wanted to make it a little bit more understandable English sentence, I would say there's at least one person who's not wearing a purple shirt. Or I could say there is someone who is not wearing a purple shirt. Just got a little journey there. So how do I write that in predicate calculus if I want to convert it back? And now I have a there is instead of a for all, right? So that's a there exists statement. So there's a person who is not wearing a purple shirt. How do I say X is not wearing a purple shirt?
Not p of x.
Not the quantity P of X. So I put not P of X. And these two things are logically equivalent. So we've just figured out for ourselves what De Morgan's is for quantifiers. These symbols, the for all and the there exists, they're called quantifiers. And they're called that because they're telling us when or how often the X is going to make our statement true. So it quantifies the statement. So let's write this on another sheet and just talk about it a little bit more. So we've just shown that for all x, if I negate for all x p of x, that's logically equivalent to saying there exists x so that p of x is false. So this is De Morgan's again. So De Morgan's is basically all the rules that let us apply nots and move them around. Anything that does that is called De Morgan's. He did lots of work with logic. Okay, so if you had to guess, what would you think would be logically equivalent to negating a there exists? A for all, and then what?
Not P.
Not P of X, and that's true, actually. So if I said it is not true that there is someone wearing a purple shirt, then that means that everyone must be wearing something besides purple. Right? So if I want to figure out how to write there exists x p of x, not, I write there exists x p of x. There is someone wearing a purple shirt. If I wanted to write a not for that, I would say there is no one wearing a purple shirt. And then if I wanted to change that to talk about what everyone is doing,
Everyone is not wearing a purple shirt.
then what I know is true about everyone is that everyone has something besides purple on. So that would be for all x, p of x is false. Everyone is wearing a non-purple shirt.
Everyone is not wearing.
I'm sorry, I'm making up my own words. Right? Or I would say, it's true that everyone is not wearing purple. It's a little bit confusing, right? So usually in English, we just switch between and use the one that's the least confusing for talking, or at least we try to do that. But we might, sometimes these might be, we might need one or the other, and we need to be able to convert back and forth in logic. So now let me ask you a question. The question is, does it matter where the not goes? Is this statement and this statement, are they the same? Not the same at all. It's just like the difference between where the not goes with ands and ors, right? So ands and ors are not the same at all. Just because this has a for all x in it and a not doesn't mean it's the same. The order really matters. Because this is logically equivalent to there exists, right? This is there exists x, not p of x. And then it's really easy to see that these are different. So De Morgan's, if you remember, when we did De Morgan's, whenever we applied De Morgan's when we had P and Q, and then if we negated that, then we negated the variables and switched the and into an or. I can remember the same rule with De Morgan's here. If I apply a not to the for all, I switch it to the other quantifier, and then negate everything on the inside. Yes?
When you're using this notation, can you use the bars?
I don't normally use the bars, but you can.
Okay.
So you can combine the notations if you like. The only notation I don't like for knots is the quotes, because quotes look like random scratches on your paper. And you might miss them, or I might miss them, or you might put lots of random scratches on there if you don't know the answer. So I would much rather use any other notation besides the quotes. I don't think any of you would do that on your homework, but other people have in the past.
But it is easier to use the quotes in the computer than these other
It is easier in the computer, and that's fine because there shouldn't be any random marks on your nice, clean computer paper. Okay. It's fine. If you're doing your work on the computer, the quotes are fine. Okay, so now that we've learned this rule, let's get a little bit of practice using it. Actually, let's talk about combined quantifiers. We're not gonna talk about what this means yet. So after the for all x, after that all the x's go with the for all x, and after there exists y, all the y's go with the there exists. So in this case, suppose I want to do De Morgan's on this statement. Okay, if I want to do De Morgan's, what would I do? I would change the for all into there exists and then negate the contents, right? So I would get there exists x, not the rest of the stuff. So I'm going to do this one step at a time because then I won't make any mistakes. So then if I apply De Morgan's again, I get there exists x, and this not applied to the there exists gets a for all y, and then I negate the contents, which is p of x and q of y. And then I can use De Morgan's again, which is our regular propositional De Morgan's rule. And I leave the quantifiers the same. I get not p of x. The and changes into an or, and I get not q of y. So there's an example of doing multiple steps of De Morgan's on a line, so I can negate the entire line. So the next thing we're going to do is we're going to talk about what does this mean for all x there exists a y. Just everything that we've been doing so far, it matters the order, I'll answer you in a second, the order that we do things really matters. So in this case, the fact that the for all x comes before the there exists y is very important. We're going to talk about that in a minute. But first, Jeff has a question.
If we're doing De Morgan's on a proof, and we have the top line, can we go immediately down to the fourth line? Or do we have to do each successive step of De Morgan's on a proof?
I don't mind if you go right down to the bottom line after you get some practice.
Okay.
Okay? Just be careful and double check yourself. Make sure that you flipped all your quantifiers, all the variables are negated, and all the ands are negated into ors. Okay, so just double check your work. If you're going to skip steps, you should always double check because I won't give you partial credit if you mess up. Okay? Because I can't see where you stopped, where you messed up. If I can figure out where you messed up, you'll get partial credit. All right, so we're talking about order matters. So if I say for all x, there exists a y, and let's talk about a statement that depends both on x and y. And let's say that p of xy is equal to has to start with a p. X pretends to be y. Okay? I just made up that function. I hope it's not too retarded when we do this example. Okay, so in this case, this statement said, this is the way I read these. For all, I read as a for each. For each x. And there exists a y, I read is there. I read it as I can find a y. So if I read this statement, I read it to say, for each x, I can find a y value that makes p of xy true. That's how I read this statement right here. For each x, I can find a y value that makes p of xy true. Now in this case, if p of xy is x pretends to be y, and let's say that x and y are people, okay, they don't have to come from the same domain, but I'm telling you that they do in this case, then that means for each person, then there is another person. So for each person x, I can find another person y so that x has pretended to be y. Okay? And actually, let's just make this a little bit simpler and change it from pretend. Let's just put likes. Okay? Even though p of xy doesn't start with an L for likes.
Is that like saying every person has one and only one best friend?
No, it's not. It's saying at least. It's kind of
At
like
least one best friend.
So in this case, if I read it again with the likes, for each x, I can find a y so that x likes y. So that means every person, there's someone out there in the world that they like. Okay? Does everybody have to like the same person? No, everyone can choose someone different to like, right? I can like my brother, you guys don't have to like him. Or vice versa. Right? So in this case, each x has a y value, and that's why I read it like this. For each x, and the x is the most important thing because it comes first. It's the independent variable because it came first. So it gets assigned before y does. So if you think about in a program, when you're doing assignments or you're doing a loop, like the for all is just like a loop for every single possible value of x. And this assignment comes on the inside, so that means it can depend on the x value. Right? So y depends on x because it comes second. Now let's reverse the order of this and then see what it means. So if I say there exists a y for all x, p of xy, then this says there is a person, I can find a person y, so that for every person x, x likes y. How many y's are there?
At least one.
There's only one person that's getting liked, right? We'll just talk about one. There could be more than one that everybody likes, but let's just talk about one. There's at least one person that everyone likes, no matter who x is, that same y is going to work for the statement. So In this case, X depends on Y because it comes second. So Y is independent because it comes first. So in this case, there's about one Y value that makes this statement true. There might be more than one, but we'll just say there's at least one. So I'm just going to compare numbers of things. If I have for all x there exists a y, how many y's are there that help make this statement true?
Whole population.
There could be lots, right? So there's possibly as many y's as there are x's. So these statements are very different. It depends on where you put the there exists and where you put the for all. Okay, so we've figured out that where the not goes matters and what order the quantifiers in matters, and it also matters which letter you put where, right?
Tiffany, how do you read that statement at the top?
This statement right here?
The one above it.
This?
Above it. That one.
Yeah, that's the same statement as down here.
Oh, sorry.
But I can find a person Y so that for every other person X likes Y. So I have to read this. I always have to read this as X likes Y. I read this as I can find, and this is a for each.
So basically, there's a person who everyone likes.
Right. So there is a person who everyone likes. That's a perfect English sentence for that. So that's a lot different than saying everyone can find someone that they like. Right? There's a person who everyone likes that's one person.
How could you prove that, though?
How can I prove that they're different?
Well, no, how could you prove that there's one person that everyone likes? I mean, that's like, isn't that going to like infinity? You could not.
Well, I could restrict my domain to a room full of people, and then I could ask everybody who they like and find out if there was one person that everybody liked. Right?
Okay, so it depends on the set.
It depends on the universe that you're talking about. So since we were just talking about whether these two things were the same, I didn't quantify the universe. But if you really wanted to find out, you would need to know. Okay, but a lot of times we don't need to know whether the statement's true or false. We just want to figure out if combinations of these propositions together are going to be true, or when some combinations imply some others. So some of the rules that you've been using can still be used here. So for example, if I have if I know for all x p of x, and I know for all x p of x implies q of x, I can use implications and ands and ors with my predicates. Okay, if I know those two, you all know a rule that will tell you something else true. Modus ponens, right? So if all the p's are true and all the p's imply q's, then I know that all the q's must be true. Right? So this logically implies for all x, q of x. With for alls, you can do logic and just ignore the for alls. As long as everything is true for everything, then I can just not even think about the for all x anymore. It's there exists that give us trouble, right? If I have there exists x, p of x, and for all x, p of x implies q of x, I can still use modus ponens, but I have to be careful. Right? What happens when I use it? Remember that an and preserves falses, right? So a lot of the time, this thing is going to be false. It's only going to be true for one guy, right? And this is true all the time. So my resulting statement should have as many falses as this does. So it should have a there exists. So if P is true for one guy and P implies Q is true for everybody, then Q must be true for that very same guy. So sometimes I even label this X as 1 to remind myself that it has to be the same as the person that got quantified in this statement. The person that has Q true must have had P true.
Does that rule have a special name or anything?
This is modus ponens. It's the same thing,
Same thing, okay.
but there's no special rule for it, but I'm just saying that whenever I combine a there exists and a for all, I better get a there exists because I'm anding. If I did an or, it would be a for all, right? Because ors preserve the truths.
Can you repeat that again?
Ors preserve truths. So if I have like 1 or anything else, I'm going to get a 1.
Okay.
Right? So if I did there exists X, P of X, or for all X, Q of X, then I probably wouldn't really combine these. I'd leave them separate because it wouldn't tell me any new information to combine them.
Okay.
But if I were to combine them, I would say for all X, either P of X is true or Q of X is true. This would logically imply that just by the definition of or, and by knowing that or is going to combine and make sure that all of these are true. So this or statement is always true.
And what was the reason for the above ones?
This is if that was given. I mean these two?
No,
This?
yeah.
Modus ponens is the reason.
Okay.
And the fact that this there exists there is by the definition of how there exists works and how and works. So I don't give a reason for that. I just know that if I use it, it can only be true for the things. This statement can only be true where P has to be true and P implies X has to be true.
Right.
And this only happens where it happens to be X1, so this has to be for X1.
Okay.
Because this is automatically going to be true for X1 because it's true for everything.
Okay.
Does that make sense?
Well, that's what implies means, right?
No, that's
P
what
implies
for all
Q.
means. For all means no matter what X I plug in, this statement will be true. P implies Q will be true.
Okay. I got you.
So we're doing a lot of complicated combinations of things that you've done so far. So you have to keep them straight. Okay, so let me just list what we did today. To remind you, we did some circuit design. Remember that a multiplexer is a switch, okay, using the control bit. And we also, I think multiplexer actually has an E there. I'm always misspelling multiplexer. So we also talked about adders and binary numbers. Okay, and I want you to be able to understand that. So the book has also a discussion of the adder problem in Chapter 9, so take a look at that. We started with our predicate calculus definitions. We had for all X and there exists X. And we talked about De Morgan's with those. And also how combinations work. So the order matters with those, and left to right is how we read them. So if I had there exists for all X for all Y, this means I can find an X so that the statement's going to be true for all Y, whatever the statement happens to be after that. So order really matters with these. So we worked with converting from English to logic and logic back to English. And you're going to have to do that on your next homework. And your next homework is posted, and you should be able to work a lot of the problems already on that homework. So we'll do, next time, we'll finish up everything that you need for doing that homework, which means that we're going to be doing some truth tables with predicate calculus. Since they're propositions, we can do truth tables with them. And we'll figure out how to use them together and make a truth table and be able to find out when combinations of statements are going to be true. Okay, have a good day.